Okay, welcome to this informal Python tutorial on multidimensional analysis, some data visualization, and I'll kind of walk you through a few other things as well. So I will go ahead and share my screen. Okay, we've got one person logged into the hub. Excellent. Okay, so hopefully you can all see my screen. This is what the Jupyter Hub should look like when you log in. Well, actually, it will be in this folder here, COESSIN 2022 Hub. So I hope most, if not all of you, have seen the pre-workshops that we held last week or attended Daniel's workshop yesterday. But just, it never hurts to go over things again. So I'll just mention, so this is Jupyter Lab. This is the interface called Jupyter Lab. On the left here, we have the list of folders and files. So these are notebooks. And we can open anything here by double clicking on it. So today we're doing multidimensional analysis. So I'll double click on that. And just going to make sure this is the updated one. Yep, great. I just updated it before. And you can see over on the far left, there are other options. So this folder icon is where we can see the list of folders. You can also click this kind of stop button. This shows you what tabs are open. So we can see over here, we have two different tabs. One is this launcher, the so-called launcher. From here, you can launch a new notebook. So if you click Python 3, it will launch a new notebook for you. For later in the week, you might use Julia, which is a different language. So you can see here, this is opening a notebook that runs Python. This one runs Julia. You can open up a few other things like a terminal or just a regular text file, and so on. You can read what they say. So these list the open tabs. We can close them all here by clicking close all or by clicking these X's. And then the kernel is what is actually running. So right now we have one Python kernel and it's running this multidimensional data analysis. So I could click this and it will shut it down. There are a few other tabs here that we're not really going to use. You're welcome to explore. But mostly it's this folder here that's useful. If you want to go navigate, let's see, I just added these yesterday, labs from 2021. So these are labs that I will not be that we will not be going over this year, but you can check them out yourselves from last year just for some more content. But if you want to go back a folder or even back to your home folder, you can just click at the top here. So I'll go back into our COESSIN 2022 Hub is where all of the Python labs are for this year. Okay, so that's just a little walkthrough of how Jupyter Lab works. Let's see what to change that. Let's do that. Okay. So we are going to talk today about multidimensional data analysis. So here, some of the learning objectives is kind of what is multidimensional data and well, how is that different from not multidimensional data? We're going to be using a package called Xarray. So we're going to go through the basics of Xarray. We're going to do a little bit of plotting with Xarray. And then I'll do a very brief introduction to Dask, which is a package that allows for parallel computing. So a lot of what I'll talk about today is especially useful for larger data sets, which you can access and handle much easier on the cloud, like our Jupyter Hub that we're running right now. And a bonus objective is I'm just going to walk you through, because we have access to this, this Jupyter Hub that you're all on right now. It is actually part of the Pangeo Cloud project. And Pangeo has a bunch of data sets that are accessible from the cloud. So I'm just going to walk you through some of those data sets that you can access on your own right now, and you can start analyzing if you want. A lot of what I'll talk about here is from this great online book, An Introduction to Earth and Environmental Data Science. I have this tab open here. Yep, thanks. I'll Actually might make Daniel co-host. That way you can help with muting if that is necessary. Okay, so this is the book. This is called a Jupyter book. So it actually, so here we can just see there's a lot of text. It has all of this written out, but on the left here is a table of contents. It has an introduction to Jupyter Lab. It goes through some of these basic packages like NumPy and Matplotlib. And you can see here that it actually has code throughout the book. So it kind of intertwines code and text, which is really nice. So that was the inspiration for some of what I'll be showing today. Okay, are there any questions at this point? Again, please feel free to interrupt at any time with any questions or type them in the chat and Daniel will monitor that. But this is your time to ask any questions. Okay. I don't hear any questions, so I will keep going. So I'm just going to click this folder again, and then I get rid of that sidebar just so I have more space on the screen. And we're going to dive in. So I've mentioned that this is about multidimensional data analysis. So what does that mean? So in the climate sciences, we often refer to tabular data versus multidimensional data. So tabular data looks something like this, where we have rows, observations, and then we have columns. So this is for some of you basketball fans out there. You have player A, B, C. They have this many minutes on the court. They made this many points, rebounds, assists, and so on. So in a climate or ocean context, these observations might be locations. Let's say you're going around and taking measurements of temperature and humidity at different points on a lake or something. So you'd have different geographical points here. So these might be different locations. And then your columns could be something like the temperature that you measured at that location, the humidity, the precipitation, the wind velocity, anything like that. So that's kind of where we have this tabular data. And you might have seen this if you joined in some of the previous Python sessions, and they talked about the package called Pandas. So Daniel mentioned it yesterday, and Oladipo mentioned it in the pre-workshop last week. So Pandas is a really, really useful library for this kind of tabular data. But this tabular data doesn't always work well. So in climate science, we often have data that depends on many dimensions. So let's say we have the Earth's surface temperature. So we have T is a function of X, Y, and T. So where X would be one dimension, let's say longitude, Y would be another one, which would be latitude, but we also have that at every point in time. So time is also a dimension. This is very common for satellite data and model data. So here we have this multidimensional data. So we have something like this. So now we've got our temperature data. It's in 3D because we have X, Y, and time. It has, so these three dimensions, and it has this latitude and longitude, which are actually, if X and Y were just numbers, 0, 1, 2, 3, or just an index, the latitude and longitude tell you what the actual values of the locations, what they are. So in X-array, we call these coordinates, we call these dimensions, we call these variables. And you can have multiple variables within one data set. We'll see that in a second. So that's terminology is a data set with multiple variables that all depend on the same coordinates and dimensions. And then we have a data array would be a single variable. So this is just some terminology that I'm going to throw out. Are there any questions yet? Okay. Please do chime in if you have any questions. I can't see all of you on the screen because while I'm sharing, so I won't be able to see anything. Okay. So let's get started. Let's load a data set. We're going to load a data set that is stored in the Pangeo data catalog. which we have access to from this hub. So this particular data set is one that I am using in my own research. It has 41 years of data, and the model is called the Community Earth System Model. We'll just be loading the ocean portion for this oceanography school. And the ocean is called, the ocean model itself is called POP, which is the Parallel Ocean Program. So I'm saying we're going to load a data set. I don't actually mean we're going to load it in right now, because this is a very, very large data set. What we're going to do is we're going to do something called lazy loading. So we are actually only going to load the data set metadata. So if you're unfamiliar, metadata is basically the information about the data set. So that will tell you things like which variables the data set contains, what size those variables are, what the names of the dimensions are. You can have units, you can have all sorts of things. And metadata is very small because it's just text that describes the data. And this is, as we can see here, this data set is 5.6 terabytes, which is absolutely humongous. And we are not able to load that even close into memory. But most of the time, we don't actually want to load an entire data set. We might be just interested in the surface temperature or a specific region of the globe. And so we don't want to have to load in all of this data because that would take a very long time. And it's actually just not even feasible. We don't have that much memory. So these packages called Xarray and Dask and a few others allow us to load lazily. So we can load the metadata, which means we can see what data is available, and then we can decide when to actually do the computation. Okay. I don't hear any questions, so I'll keep going. So let's go ahead and do that. We're going to use this package. So if you've seen some of the previous sessions, you'll see that we have to load our packages or libraries or modules. They're all kind of the same thing. First, so I'm going to load something from intake. There's a link here if you want to learn more about intake. It's all about how to access data. So here we're going to use intake, and I'm saying I want to open this catalog that is here. And we can see it's on this Pangeo data store. So this is Pangeo Cloud Data Catalog. And we're going to load the CESM POP model. I'll show you later on how I know what this URL is. So for now, just accept this, but I will show you how to find this URL and how you can load in different data sets yourself. This second line here, under CESM POP, there are actually quite several different data sets of different runs of the model. And I'm saying here that I want the high resolution control run. So high res is just how they're calling high resolution. Control meaning I don't want any climate change in there. Okay, so I shift return. You can see this little star on the left. That means that it is working, and now we have a 1. So now it is loaded, lazily loaded. Okay, so let's use some Xarray. We can view the data set that we just loaded by just typing the name. So we just called it DS for data set. So I'll say DS here. If I just run that cell, it will print out information about the data set. So we can see first, it is an Xarray.dataset. So if we go back up to this, it's this data set here. So it's multiple variables and coordinates and dimensions. And we have a list of dimensions here. So we can see we have nlat, we have nlon. So in this case, that means the number of latitude points and number of longitude points. So these are not actually the values of latitude and longitude. We have almost 15,000 time steps because it's daily data for 41 years, which is pretty large. And we have a few other dimensions that are in the Z direction. We can see all the data variables here, so we can toggle these. This is all kind of interactive. And we can see the list of variables here. So if you're not familiar with ocean data, you might not know what these mean. That's okay. We can look at it. So let's see what this HMXL_2 is. We can see that it depends on time, nlat, and nlon, so it's 3-dimensional. We can see the type. This means float, which basically means it's decimal. They're decimal inputs. And then we can see here that actually says Dask array. I'll mention this later, but this kind of means under the hood, we are loading in a Dask array. And I'll mention this later when I talk about Dask. But over here, you can see this little icon that's looks like a little piece of paper, and it says show and hide attributes. So if you click on that, it then tells you information about this variable. So most importantly, it tells us that the long name is mixed layer depth. So if I'm not familiar with that, I say, okay, mixed layer depth, great. There's a mixed layer in the ocean, it must be how deep that is. And it tells us the units, also very important. So centimeters. There's another little icon over here, which looks like a stack of cylinders. And if I click on that, it shows me the shape and size of the variable. And it has a little nice diagram over here. So this is the visualization. We can see that there are almost 15,000 time steps. We have 3,600 up here in the longitude, 2,400 points in latitude. And here it actually tells us how big this is. So this single variable is 480 gigabytes. That's very big. That's just one variable, and you can see there are like 10 variables. It tells you the shape. This tells you how many tasks there are for Dask. Again, I can talk about that a bit later. And here, so this is for the full array. There's also listed here a chunk. Chunking is very important for big data sets because because our memory and computational power cannot process, for instance, 480 gigabytes altogether. We have to chunk our data up. So basically put it into little pieces that we can operate on. And so here, this data is pre-chunked. All of this data on the cloud will be pre-chunked. And this is what the chunks are: 32 megabytes, which is much smaller than 480 gigabytes. And we can see the chunk size. So it says 1 here, comma 2,400, 3,600. The 1 means there's only one time step. So each chunk is just a single time step. So anyway, I'm getting a little into the weeds about all of that, but that's what all that means. And you can click on any of these and expand them and see what they are and what their size is. So that's really useful. You have a huge list of coordinates here. So these are all different values relevant to the data. Some of them, like here, if it just has these 2 parentheses, it means just a single number. Again, you can click here to see what it is. It says acceleration due to gravity in centimeters squared per second. So you have all sorts of different things here. We can close that. I'll close the data variables. And you also have attributes. These are kind of all of the other information you might want. For instance, this one is very handy. It says calendar. Each model uses its own calendar convention. And this one, for instance, is all years have exactly 365 days. So that means that the data here, thanks, Daniel. None of the data here has a leap year. So there's no leap year in this particular model, but it has a lot of other interesting things that might be relevant. Okay. Anyone have any questions or points of confusion so far? No? Okay. Again, I don't know if new people have joined, but please do interrupt and ask any questions that you have. I'm happy to answer anything. And hopefully you're all able to follow along. And if you're not, post in the chat, interrupt me, anything is fine. Okay, so I just kind of walked through a lot of what I was talking about here. To access a specific variable, so we have the data variables here. I'll go ahead and close these so you can see them all. So let's say we want to access temperature, surface temperature. So I know that from working with ocean data that SST usually refers to sea surface temperature. I can double check that. And yep, surface potential temperature. It even tells me the units, degrees Celsius. Great. So if I just want to access that variable, all I have to do is type DS, which is the full data set, and just do .sst. So if I shift return that, it will give me information just about the SST variable. So now we see instead of a data set, we're accessing a data array because it's a single variable. And it has the information that we just saw above. So this is everything that we could see up there, but now we're just seeing it for SST. We can take a look. We don't have to, if this is accessing a variable, we can also access dimensions and coordinates. So here I'm accessing the time coordinate, ds.time. And this will tell us what the time is. So we can see here it uses this CF time. This is a Python library for denoting time. And you can see here it has date, time, no leap. We already saw that. It doesn't have a leap year. And then we can see that it has year 46. 1 would be the month and 2 would be the day. So it starts on January 2nd, year 46. So those are not real years. These are model years. And then you can see this ... here. And then it ends at year 87 on January 1st. So that's how we can see what the time is here. We can list all of the dimensions by doing ds.dims, and then it just lists them out. Now, if we scroll back up to here, they're listed out here as well. So this is just another way to access those. So let's kind of grab some of the data. So we have here, let's say we want to just grab 1 day's worth of data. So we know that it's time, X and Y are the 3 dimensions. So how we can do that is we say ds.sst. So we're grabbing sea surface temperature. And then we use this .icell function, which selects the time based on an index. So that's why it's icell, it's like index selection. So I'm saying I want the first time step, but because Python starts counting at 0, then you have to say time equals 0. And let's see what we get. Okay, so now we can see that because we have 1 time step, we no longer have a time dimension. So now our array is just this 2D block rectangle here. But notice that so far it's still giving us just the metadata. So we haven't actually done anything with the data yet. If you want to select more than 1 time, let's say we want to select the first 10 days, for instance, then I can use the same index selection and just say time equals and then slice. And I can slice this from 0 to 10. That'll give me the first 10 time steps, and we can double check that. If I run that, sure enough, time, there are 10. Oops, sorry, I'm gonna have a lot of emails. I have another summer school that I'm helping organize in 2 weeks. So that's how we know that we've selected 10 time steps.
Hello, Paige.
Yeah.
Yes, so Adiola has a question. I think it will be best if you answer it. I can read it out if you cannot see it. He's asking, he wants to find out if you can use the same functions to read netcdf files. Yeah, good question. Yes, you can use all of this to read netcdf files. The only thing that would potentially be different is this here. So instead of using intake to load your data, you would use xarray. So import xarray as xr, and then it would be something like, yeah, data set equals xr dot I think
load
maybe open data set or something.
Open data set, yeah, something like that. And then you'd put your path to data here, and you could open it that way. And then it would look, everything would look very similar. So in fact, it'd look identical. You'd have this same view and all of that. That's good.
But since we don't want to charge the data into our computer, open data set, for example, will not charge it. I mean,
Yeah, open data set does the same thing here. It will do the lazy loading. So that's Xarray is all about lazy loading. So if you open the data set, it will just grab the metadata initially, and I'll show in a little bit. It's everything is the same as here. You don't actually compute it until you tell it to compute. So it'll do the same.
Okay.
Yeah, good question. Okay, just gonna make that markdown so I don't accidentally run that because it won't run. Okay, was that clear? Are there any more questions about this? I really need to turn on my do not disturb. Great. Now you don't have to keep seeing all my messages pop up. Okay. Cool. Good questions. Thanks for asking that. Oh, we have another one. Okay, great. Okay. So we just kind of grabbed a slice. So everything here that I'm talking about will be the same for any NetCDF data. So that carries across. Let's say we want to let's say we want to actually do some computation. We want to take the mean across time. So we want to take every time step in this data set and we want to average across time. You can do that very simply in Xarray. So again, we say ds.sst, so we're accessing the surface temperature. And then I can just say dot mean, and then I list the dimension over which I want to average. So in this case, time. So I could put this as any dimension. This could also be n-lon. That would be over the longitude dimension. So that's quite simple. If I run that, we can see again that the time dimension has disappeared because we have averaged over the whole thing. So if we were to do n-lon, what do we think this will be? Well, we see that n-lon is listed here. Instead of nlat by n-lon, we'd have time by nlat. So let's do that. So now we're averaging over longitude, and now you can see we have this 2400 by almost 15,000 shape, and that's because we've gotten rid of the longitude dimension. So that's a very simple way to do a mean. Again, this is all done lazily right now. So I have not actually taken an average across. It hasn't actually done any of the computation on the data points, but it's telling you here what to expect, what output to expect. And which is actually really handy. Before you run a really big computation, you can do this, make sure it looks like what you want. You say, yep, I wanted it to be in terms of time and latitude. Great. And then you can actually compute that. And I'll show you in a second how to do that. Okay, so now let's say we want to plot. Again, Xarray makes this very easy. We can do all of this in one line. So we access the sea surface temperature. We select the first time step. And then we can, oops, we can plot that. Oh, ignore what I just did. Then you can just say dot plot, open parentheses and close parentheses, because plot is a function, and it will plot it for us. So I'm going to run that cell, and I have a note here. This may take several seconds. So this is the first time we're really seeing it take a long time. And the reason for that is because this is the first time we have actually accessed any data. And so here we go. This is how Xarray plots data. This is a 2D plot. So what I was saying before is by calling dot plot, you actually have to access data. So here we're accessing that first time step, but we're accessing all of the latitude and all of the longitude points. But notice how nice this is. Xarray has labeled things for us. The title is a bit cryptic, so we'll get to that in a second. But it labels our y-axis as nlat, it labels our x-axis as nlon. It gives us a nice color bar. it labels the color bar as surface potential temperature, and it even labels the units for us. So this is all of Xarray interpreting the data and labeling these for us. Now we can change any of those if we want, but I'm just going to compare this to if I were to plot the same thing, just not using Xarray, but using matplotlib.pyplot, which is the standard plotting package. So I'm going to load that first. And now I'm going to call one of the plotting functions, plt.pcolormesh. That's one way to plot 2D data. And then I'm going to call the same thing that we had up there, and we'll see what that looks like. So again, it takes a little moment, and here we go. So this also looks just fine, but you notice we don't have any labels for our axes. We don't have the color bar automatically there and automatically labeled. We also have a different color bar. So what Xarray does is it actually is using this exact same library. It's using matplotlib.pyplot in the background, but it's just being a little bit smart by saying, well, in this case, it's saying there are negative and positive values. So there are going to be some negative values very close to the Antarctica and the polar regions. So it's saying, why we detect negative and positive values. We're going to make a color bar that is white at 0, and it's like, and diverges. So it's a diverging color bar where it goes both negative and positive. So it interprets that. It interprets the labels for each of these and labels that for us. So it's very handy, and you can see how simple this is. This was a single line, not much text at all, and we already got a plot of some of our data. So that's pretty cool. All right, now I have some exercises for all of you. So hopefully some of you have been able to follow along. So I might just give you a minute to try this first exercise. And the first exercise is where we're going to, if we scroll back up, this title is not very good. This says T0 Kelvin equals 0 degrees Kelvin, CP air, blah, 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 dot, dot, dot. That's not really a title. Xarray does a good job of interpreting some of these labels. It does not interpret the title very well. So we want to change that to something that makes more sense, like snapshot of sea surface temperature. So if you are familiar with plotting, you might know how to do this. I have a hint here, and you can toggle that on and off by clicking that triangle next to it. And you can read this hint, and it kind of tells you what to use in that hint. A bonus is see if you can increase the title font size to 24. I forget what the default is, probably 12 or something. So it's just a little small, so we might want it bigger. And again, you can toggle this hint if you want it by clicking here. If you think you can do it without the hint, that's great too. And you can write your answer here. So I'm going to start by just copying over this line. So now I have my plot line. And I'll just maybe hang out for another 20 seconds or so in case you are following along and want to try this yourself, or if you have any questions about this. No questions? This one here is a bit of a warm-up exercise, but it also shows you how if you followed along with some of the previous Python content yesterday and last week, you can use the same thing that we learned of how to plot there. You can just use it seamlessly with Xarray. Okay. I hope some of you are following along. We're not just waiting for no one. Okay, so I will go ahead and show the answer to this one. So we'll do plt.title. And then I'm just going to copy this. I already wrote, put it in quotes. You can do single or double quotes, they're the same. And that should do the trick. So I'll run that again, see if it plots. Okay, see the chat. All right, thanks, Babette, following along. Yeah, if others are following along or are, you know, need a little bit more time, please post in the chat or just let me know. So there we go. Snapshot of sea surface temperature. If I want to do the bonus and increase the font size, I just do comma, font size equals 24. Run that again, see if that works. Okay, Ozas, hello. You're following along as well. Excellent. So great to see you all. Hello, how are you, Ozas?
Hello.
Bye, good to see you.
Good to see you all.
Yes, good to see you as well.
Yeah, I'm enjoying your lecture.
Great, thank you. It's good to have some feedback because in a virtual space, I just feel like I'm talking to myself. All right, and Victoria is following along as well. Amazing. But it's
nice.
Yes. All right.
Thank
Yay.
you, Paige. We're pulling along. We're with you.
Okay, great. Thank you for letting me know. And if you are lost, that's okay too. Just let me know and I will try and help make sure that you follow along. But this is great.
Great.
Yay.
Great.
Okay. So that's the answer. Oh, Urias, following but not using Python. Interesting. As in you're using a different language or you're just following along without actually evaluating yourself. If you're using another language, I'd be very impressed. That's pretty cool. But that's fine too. And this is all recorded, so you're welcome to follow along, and then you can watch it later and follow, you know, if open up the Jupyter Hub and follow along later. So that was the answer. I also have this here. If you're going through this by yourself and you want to make sure you had the answer right, I have the answer written here. So you can't evaluate this cell, but you can copy and paste it if you want. And this looks the same. Oops, I put font size 18. Oh, well, that was my bad. I'll have to fix that because I certainly said 24 here. Well, anyway, you know how to change that font size. Okay. All right, Uriah. So you are not doing any programming right now, but you kind of want to learn. That's fantastic. That's great. I think programming is a really, really useful skill. Depending on what research or what jobs you have, you could use it more or less. But these days, I feel like what I hear is, you know, most people will want some programming skills. So, okay. So, exercise 2, I'm debating whether, let's see what the time is. I might just let you figure out these exercises. The answers are there, so you have that. That way I can continue along unless anyone has a specific question. Uriah says, is this applicable for geological work? Certainly. So this could be applicable to anything. It's probably more common in the climate space. But any data that could be, I actually don't know boreholes specifically, so that's a little too specific for me, but any data that is multidimensional, you'll want to use X-ray. And just scrolling back up. So if your data can easily be written in a table, then you're going to want to use Pandas, because Pandas provides most of the same thing, and it's actually often quite similar syntax as well for tabular data. So X-ray is very specifically for these multidimensional uses, but there are a lot of, it's not just in the climate space that you might have this. So I think it depends on your data type, whether you have these multiple dimensions, and that's not that uncommon. So if you're doing some geological work and you have a bunch of data that has, you know, an X and a Y, like a latitude and longitude, but you're also taking it in time, you already have a three-dimensional data set. And so X-array could be useful for that. But a lot of these concepts are going to be the same across Pandas or other libraries. Let's see, where were we? All right, thanks for all the questions. All right, exercise 2, I'm going to leave that to you. Whether you do it now or come back and do it later, that's fine. Okay, so now we're just going to load a different data set. You'll see that data sets can be very different. So that was one example. This is a different one. This is another ocean data set called CM 2.6. This data set comes out of the Princeton's GFDL, Geophysical Fluid Dynamics Laboratory, but is still in this Pangeo data store. So we can still access it from this hub, no problem. So you can all go and access these now and start looking at data if you want. That's one of the real benefits of this Jupyter Hub. So I'm going to open it the same way we did before. I'm going to call it DS CM26 just to distinguish it from the DS we had before. So again, I can just write it out and we'll see what we have. So very similar, we have a data set, we have a list of dimensions. You'll notice the dimensions are different. So time is the same name, but it's a different length. We have YT ocean and XT ocean. That's instead of the NLAT and NLON from before. And we actually have a YU ocean and an XU ocean. So this gets into a little bit of how climate model data works, which we can talk more about if you want. But most models actually have what's called a staggered grid. So we have temperature at some points. That's why you have the YT and XT, that's for temperature. And the U here is for momentum, U and V. Those would be at different points. And you can read more about that if you want. The reason for that is it often makes it easier to take derivatives. So it makes sense to do this staggered grid. So anyway, that's why we have these two different X and Ys. It's partly why I wanted to show you a different data set. Different data sets do things differently. Here are the coordinates. Here are the variables. You can see they are very different. The names are very different. So you're going to find this in different data sets have different names for things. But with this kind of interaction, that's okay. We can see, what does CHL mean? You click over here and it says surface chlorophyll concentration. So I know nothing about that, but it tells me what it is. It tells me what the coordinates are. And it tells me what the units are, mole per kilogram. Maybe some of you know more about what that is, but I have never worked with that before. But I can read it straight away. So that's great. We can also see how big it is, just like we did before. And actually, one thing I didn't mention before, you can see that the type here is as a NumPy array. So if you're used to, you may have heard NumPy previously, the X-array here actually uses NumPy arrays under the surface. So everything that you're doing here is based on NumPy. We just don't use it explicitly if, at this point. We don't need to because X-array handles that. Okay, so we're already on to exercise number 3. Let's go ahead and do that one. So I'm saying in one line, write the code to make a plot of the global sea surface temperature averaged over the first 5 days of the data set, DSCM26, the one we just loaded, and compare it to the previous one, which you did. So this averaged over 5 days is what you would have done in exercise 2. So in this one, we have a few things to figure out. First of all, we need to figure out which variable is the sea surface temperature. So we can kind of read through. I'm used to reading through a few of these. So this one jumps out, surface temp. We can double check that by clicking this, and it says potential temperature. So that's great. That's what we want. So I'll want to type DS underscore CM26 dot, and then type surface underscore temp. That's the name of the variable. And I'm actually going to show, let's see if this works. No. There we go. Okay. So you can scroll up and type it yourself. You can also start typing. And then if you hit the tab key, this will come up with everything, any variable that is within this data set that starts with surface in this case. So if I just did this and typed tab from here, it pulls up anything that I could put after this. So this would include, so CHL, that's the variable that we saw before of the chlorophyll. It also has a bunch of other things like argmax. That's something that's, it's not a variable, but it's something that we could apply to a data set. It tells you here it's a function. Whereas CHL says instance, which in this case means variable. So we have all sorts of options, but maybe you're like, no, it's something to do with surface. You can start typing SUR, tab again, it'll tell you you have these two options, and I can click that. So that's really handy that you can do that. Okay, great. So we did that. Now we are going to, we want to average over the first 5 days. So we're going to use this I cell, so this index selection again. And we are going to select time. This is a daily data set. Let's see, we can see that here. If we look at time, we can see here again, we have the year 181. We have the month, we have the day, and I think we actually have the time of day, but this is all the same. So now we can see that it's January 1st, January 2nd, January 3rd, and so on. So Urias asks, which one can we use to do a map? So I will mention that a bit later. You can see from our plots above that this looks like a map, but we're not using any mapping features. And the package to use for this would be CartoPy. And we don't have a CartoPy tutorial this year, but we don't have one specifically on CartoPy, but satellite oceanography, which is a lab that will be in person. So we don't have a tutorial virtually, but you can walk through this yourself. It has all of the explanations. This one uses CartoPy, so it will show you how it works. The other thing you can do is go to labs from 2021, and there's a CartoPy tutorial, and you can open that, and it has, what to do? Let's wait for that. Open. Okay, I hope it opens. Okay, oh, there we go. So this was by Josue, and he did this for last year, but he's unfortunately traveling this year, so couldn't do this again. I put a note at the top, some of these cells don't run anymore, but most of them do. And here, this will walk you through, and it has everything written out. It walks you through how to use CartoPy and how to make some really nice projections on your map. Oh, cool. Thanks, Daniel. Yeah, Daniel also used CartoPy yesterday. So you have several examples of using that. So his, yeah, you can look at his from yesterday as well, which was the Argo data analysis. Thanks, Daniel. So that's how you'd make these fancy plots. But this is nice for now because it still looks like a map and you can kind of see everything. And it's a bit quicker than using CartoPy. Hopefully that answers the question. Okay, so we're in the middle of this exercise. So we want a time average over the first 5 days. So I'm going to say time equals slice 0 to 5. So that slices the first 5 days, but now I want to average over that. So I just add a dot mean. Oops, so I can type dot mean of time. And that should give me a mean over time. So we can, as I said before we actually plot it, we can make sure that this is what we want. Yes. So I got rid of the time dimension. It's only X and Y. That's what I wanted. So now I can just add dot plot and run it again, and it will run it. So this is, it might take a few seconds again because we're actually accessing data. And here we go. So again, we can see that Xarray has labeled our X and Y for us. In this case, these are actually in degrees, longitude, and latitude, unlike the previous data set. And that's labeled for us. And there we go. It looks pretty similar to the one that we had up above, which is good. Models aren't the same, but they should be similar. Okay. Any questions up to now? Okay. So in addition to this index selection that we've been using, there's also a just regular selection.sel command. So index selection is doing it based on an index. So you say you want the 0th or the 5th index of time, for instance. .cell, this selection one, means you can actually specify what you want. So we could do it for time. Here I'm showing an example of selecting, so just .cell, based on the actual values. So here I'm saying xt ocean, so x would be longitude. I want longitude from -80 to -20, and I want latitude from 25 to 50. So this should select out the Gulf Stream. So I just looked at this when I was making this and said, oh, the Gulf Stream, oops, the Gulf Stream is over here. And I just kind of looked at what the longitude and latitude would be. So we could kind of zoom in on the Gulf Stream. And so here we go. So here's the Gulf Stream. And so I can just use that and select the actual specific latitude and longitude I want. So exercise 4 has you do the same thing, but I want you to zoom in on the Gulf of Guinea region. So I'm not going to do this one. I might give you a few seconds now, but you'll want to look at this map. You can see the Gulf of Guinea region, something around here, and you can guess about what longitude it is, what latitude, and you can basically copy and paste this line, replacing the range of longitude and latitude with the ones that you want. So give you a few seconds to do that. Let me know if you have any questions, or if you get a plot, you can give a shout. Again, you can toggle on the hint, which is basically what I just said. And you'll be able to then zoom in on the Gulf of Guinea region.
Paige, I have also a question.
Yes.
So I did that, and I wanted to know if the continent, we can change the color, for the continental area in the plot without using a cartopy or base map.
Okay, so that's a good question. So you can see here, this is North America from the Gulf Stream.
Yeah.
I'll use this as the example. At the moment, this is being interpreted. The reason, if we go back up here, the reason why these continents are white is because the data set has made them nans, or not a number. And so this Xarray and Matplotlib interpret those as white. Actually, a good question, how to change that. I actually have to double check. Sometimes these are not a number, sometimes they're just 0, in which case the white is because they're 0 and they're at the middle of the color bar. Now, I don't remember offhand this data set, whether they're 0 or nan. So I actually don't know how to change the color of a nan, but my guess is you can if you Google it.
Okay, maybe I will check it, because I changed the color map to jet where there is no white, and still I got white on the.
Okay, cool. Then that, thank you. Then that means that the continents here are nans, and nan is interpreted as white. My guess is if you Google it, this is Daniel mentioned this. This is my word of advice. Google is your friend. If you just go in and Google how to change color of nan in PyPlot. Oops, typed that wrong, but Google knows what I mean. So there we go, and it's saying with IM show. That's another way of using p-color mesh. So what's nice to know here, and why I said in PyPlot, here I'm saying, oh, we're plotting this with Xarray, but it's using PyPlot under the hood. So what you would want to search for is how to do it in PyPlot, and then you can make it work here. So that's my suggestion. So I Google things all the time. And actually my session on Thursday, I think, I have 45-minute set of just how to ask questions and where to find help while coding. So that this will be one of my main suggestions is Google, but there are some. Stack Overflows is one website that I will mention is a very good one, usually. So yeah, good question. I've never thought about that before. So then the other thing is if you use Cartopy, you can fill the continent colors.
Yeah.
And in the Cartopy tutorial, it goes through this. It's not run at the moment, but okay. So I got a question. Can we zoom with a GUI and click and drag? These are some very good questions. We cannot do that right now. There actually might be a couple ways to do this. There is an interactive plotting package that is called HoloViews. Let me Google that again. Google is a friend. Maybe it's HoloViz. So it's called HoloViz. Sorry, and HoloViews is one of the options. So this is a visualization package in Python. They have a bunch of different options. Let's see if they have tutorial maybe. So they have things like this where you can interact. I don't know if I can pull it up at the moment, but you can go through some of this tutorial. And you can hover your mouse over and it will tell you information about, for instance, these points on the map. You can also click and drag to zoom in, and you can also link things. So here we've got maybe a histogram. If I zoomed in on a portion of the map, it will zoom in on the histogram. So it's pretty fancy. I have to admit, I've used it only a couple times, so I couldn't teach you anything at the moment. Maybe next year I'll be more of a whiz at this, and we can do a tutorial. But if anyone else has used this before, you can chime in. So that's the really fancy way of doing it. I think there's also a command. I don't know if this is going to work, so we'll see. I might break things. Matplotlib notebook. I'm trying to remember what this is. And let's see if that makes a difference. If it doesn't, then we can ignore this. Okay, JavaScript error. So it's probably not going to do anything. Can't find variable IPython. Okay, so I think this command might work if you're at home. We normally say matplotlib inline. So I'm going to do that just to reset it. So I get my plots back. But Matplotlib Notebook, I think, allows for some level of interaction, but I haven't used it much. So anyway, I'm throwing that out there. That might not be helpful. And if anyone else on here knows about this as well, feel free to chime in. So that's for the interaction. I think HoloViz is the main package for that. Okay. Great. So hopefully you had some time to do exercise 4. I'll kind of let you do that. You can look at the answer, see how you did. And the answer is, I just chose some random longitude, latitude. It doesn't have to be exact, but just zooming in on the region you want. So now we're going to cover this group by. So this is a really handy function that Xarray has. I'm just going to check the time. Oh, we don't have much time left. Okay, I might go through this quickly. That allows you to, for instance, group your data. It's really helpful with like climate data or any environmental data where you have time and you want to group it by season or something like this. So you want to compare wintertime temperatures to summertime temperatures. So we're going to be using the time dimension. This group by function, by the way, is almost identical to Pandas. So everything you're learning here can be applied to Pandas as well. It's the same. It's dot group by and it does the same thing. So here, let's group by month. I have a list here of different groupings. I don't even think this is exhaustive, but here, this is where it will interpret your data and know what month is what and which season is which and all of that. So we're going to say dot group by, we're grabbing the surface temperature, dot group by, and we're going to say accessing the time dimension, and then doing dot dt dot month. So this is kind of an internal X-array shortcut for saying month. So it interprets what the month is. And if I run that, we see that it is a data array group by object grouped over month, that there are 12 groups with these labels 1 to 12. So this would be January, February, and so on. So it tells us what they are. So now we have this object. I want to, so we have this object. It has all of the Januaries grouped together as all of the Februaries over all of the years that we're looking at. So I'm just going to access the first one. So I want January. And then I'm just going to select the first time step. Otherwise, it gets too big. So that's just me selecting the first of the Januaries, the first day of all of the Januaries. And then we can plot that. This might take another few seconds. So this is saying, take January. I'm just going to take the first time step here. Often you would average over January, but that takes a lot more time to run. So I'm not going to do that right now. That's great. That looks like kind of what we want. Now let's, just as another example, let's take a day in July, month of July, which is 7, and subtract it from the month of January, which is 1. And again, I'm just going to select the first of those just to keep things small for this demonstration. But often I would average over July, all of the Julys and all of the Januaries, and then you get kind of the difference between those averages. Okay. I was wondering if this would happen. So this is saying the kernel is restarting. So what happened was I ran out of memory. So you can see at the bottom down here of my screen, the memory, it says here how much memory I have used and how much memory I have available. So we all should have about 7 gigabytes, which is what's listed here, in our, when we run anything. I'm running, because I'm running with some pretty large data sets here, I'm actually running out of space. So I apologize for that, which is fine. So what happened was it restarted the kernel. If I try running this again, we're going to get an error, and it says DS CM26 months is not defined. That's correct because it had to restart. Notice the 1 here, which means this is the first cell evaluated. So now I apologize for this. You have to go all the way back up. You have to load this data set again. So we have to define DS CM26. Now we have to define this month thing that we just defined here. And now we can see that we started at 400 something megabytes. We're already up to 600 something just because we're running some things. So we are loading a few things. Okay. And now I'm going to run that. So I apologize for that. This actually happens reasonably frequently in this kind of situation. When this hub, you only have 7 gigabytes. I can't change that at the moment, but at the end of this week, I will show you all how to keep access to this hub, where we will basically migrate you over to the Pangeo hub, which is maintained, and you can use that as long as you want. On that hub, you have options. So when you log in, it will say, do you want small, medium, or large? So a small is about 7 gigabytes. If you are dealing with large data sets like this, you might want a large one, which is like, I forget, 12 or 16 gigabytes. So anyway, that's a little side note. Okay, so here we now have this interesting plot, and this is kind of what we expect. So we're saying take the July month and subtract January. So in the Northern Hemisphere, July is in the summer and January is in the winter, which means the July temperature should be much warmer. But in the Southern Hemisphere, the seasons are reversed. So we're taking a winter month and subtracting a summer month, and so that's why we're getting negative. So anyway, so we just did a little fun calculation and got a nice little plot. I think I will let you read through this coursening and do exercise 5. I'm going to do a walkthrough of the Pangeo data catalog. And I just realized that I did not link it here. So I will update that. Sorry for that. I meant to have a link to the Pangeo data catalog. You can see I did not finish writing my thought. Okay. Well, I will update that. Instead, we're just going to open up a new tab and type Pangeo data catalog. And it's this first hit that's not an ad. Pangeo data catalog, yay. And it says it's here at catalog.pangeo.io. And here we are. Okay, sorry, another drink. So this might look familiar. This is what we used to open the data sets earlier. We used intake, we used this open catalog. So this would be a way to open up and get a list of all of the data in the Pangeo catalog. We could do that from our Jupyter Hub, or we can just click Browse Master Catalog and it'll take us here. So here's a list of all of the data sets that are currently available on the Pangeo cloud. I have to give a warning that this catalog at the moment is a little out of date. So I think most of the things are here, but they're currently working on updating this. So in the next few months, hopefully, there will actually be a new catalog. But anyway, this is what we have for now. So let's go into ocean. Let's look at some ocean data. This is oceanography school. But you can feel free to explore any of these. All right, it is loading. Just let that load. Okay. So here we go. So it says child catalogs, which basically means individual kind of data sets. So we have a list here. We have some altimetry. So this is satellite data, or I guess radar altimetry products here. This is CESM POP. This is the one that we used at the beginning of this tutorial. So I'm going to click on that really quickly. And you'll see here, it says this is how you load in Python. So this is exactly the same. Just going to go back, go right to the top, load the data set. So we saw, you can see this here with this CESM pop.yaml. This is the same thing. We have this CESM pop.yaml. So this is where I got that line of code. I didn't know this URL off the top of my head. I just copied and pasted it from here. And you can see here that there are two different data sets. There's this high-res control. As I said, that's the one that we ended up using. So I'm saying use this high-res control one. Oops, sorry, Zoom is in my way. But we could have also used this high-res RCP 8.5. That is a climate change run of the model. So it's the same model, just with some climate change forcing. So if we click on here, this sometimes takes a little while, so it can be a little slow. But this is basically how you can right now go through this catalog, copy this load in Python text, and you can load the data sets that you want. So this is exactly what I have written here. I literally copied and pasted it to make that happen. So, and here you can actually see it has a little bit of information. It has this X-array interface. So it actually has all of this metadata written here for you. So you can just come here and be like, oh, I wanted sea surface temperature. Do they have it? And like, oh, let's see, SST, is that what I think it is? Yep, that's surface potential temperature. Great. So this is really handy to use. So Babette's question, Pangeo only works with YAML files. So a YAML file is actually basically it's a configuration file. So this .yaml is kind of like for metadata. So all of the files that you're seeing here are in what's called a ZAR format. I'm going to pull that up. ZAR. So ZAR is a format that is really great for cloud stored data. So this, Zoom is still in my way. This data set that we were using, close a few of these. that we were using, this one here, started out as netcdf files. This is the NCAR is the institute that ran this model. That's the National Center for Atmospheric Research. They produced output in a bunch of netcdf files and had them stored on their own servers. What we have done to make it part of this catalog on the cloud is we've converted all of those netcdf files to ZAR. And ZAR is really great for, as it says, chunked n-dimensional arrays. So again, this multi-dimensional arrays. So it's particularly good for this kind of thing. And it's really good for cloud optimized data. So that's actually the format that all of this data, all of these data are in. But as you can see, it actually, in this case, if you're just reading in data, it doesn't actually matter what format they're in. I showed you how you can use Xarray to load in this netcdf file, but once it's loaded, you just use it in this Xarray format. So the .yaml is not a type of data storage. This is just basically a metadata configuration file. Maybe that was more information than you needed. I hope that makes sense.
Okay, yeah, so that means you are the one to configure your, first of all, this should be my question, yeah. You are the one who configure your YAML file to be written into Pangeo, right? Or that means, for example, you create your YAML file, you put your each name, like the name of your data, the directory, stuff like that. And then you give it to Pangeo, right?
Yes, that is mostly true. So if you have a data set that you want to add to Pangeo, first of all, if you have a very small data set, you can just add it to your home folder. It's not really good practice to add data to your home folder, but if it's really tiny, if it's a few megabytes, that's the way to do it. If you have a model run or some observational data that's bigger, you can add it to the Pangeo cloud, but it's not trivial. It's not an easy thing to do. And so there's actually a kind of infrastructure that helps you do this called Pangeoforge. So we're getting a little bit kind of specific here, but Pangeoforge is a way to convert your, for instance, netcdf. I think actually at the moment it only works on netcdf files, to convert your netcdf files to ZAR and upload them to the cloud.
Okay.
And you can actually do this yourself right now. This is kind of showing how it works. I have done this a couple times. I just got a comment. This is a lot. Yes, this is a lot. My apologies. There's a lot to learn. There's a lot of stuff going on. But for now, most of you probably don't need to know this, but take a look here. It has documentation, and it has kind of how, actually, does it have a catalog? It has how to do this. Okay. So here is actually, I'm going to add this to, this is relatively new. I'm going to add this to Notebook. This is another catalog of data sets that are accessible from the Pangeo cloud. So I'm going to pull up this CESM ATM 025 degree. This is one that I ran on Pangeoforge to get on the cloud. So this is daily atmospheric data from the NCAR model. This is the run name. So it's a little bit cryptic. Let's see what more details. See, look, maintainer is me. Wow, I didn't know this existed. This is new. This is one that I have added, which means you can all access it as well. I will actually say that you can see here the most recent run failed, and we're currently debugging at the moment. But there's at least there's a subset of data that is available that you can access, and you can see this. Some of these other ones might be more, let's see, NOAA optimum interpolated SST. So this has a bit more, better description. Analysis ready ZAR data sets derived from NOAA. You can see who the maintainer is. He's actually someone who works in my lab. Okay, so it doesn't have any information here. But anyway, this is available for you to access.
Okay.
What I don't know is how you get the code to access it, but anyway. That's
Thank you.
anyway, sorry, that was probably too much of a diversion for lots of you. Sorry. But anyway, you're learning some little,
Mm.
you know, different options that you have. So I think what's real benefit is if you are at all interested in using some of these big climate data sets or some of the satellite data that's on the cloud, I really recommend at the end of this week, make sure that you get in touch with me and that you follow the instructions for how to gain access to the Pangeo cloud, because then you will have access to all of these resources at your fingertips, and you can do research and all of that kind of thing. So,
Yeah,
okay.
I will see you. I will write you.
Okay, that'd be great.
Thank you.
Okay, any other questions? Okay, we have a few more minutes. Oh, I did. There's another one. Oh, okay, John, so you tried last year but didn't get access. Okay. I'm sorry about that. I think I know a bit more about how that works now, so I can try and make sure that doesn't happen. I think I'm probably going to ask for a list of people from this school of who wants access so that I can personally make sure that you get access. But if you don't get access again, or if you're confused or something, please do contact me on Slack or by email and make sure, because we want to make sure that you all do get access and if you want it. Thanks for bringing that to my attention. So I'm going to show you a couple more things. One thing I realized I didn't include is how here I'm showing you plotting was the only way we actually accessed data. So I'm just going to add this in. So I'm going to do time again. So if you just want to compute the values, but you don't want to print anything, I'm going to say DS, I'm going to select time equals slice 0 to 5. And then I'm going to mean over time. So again, if I just run this, oh shoot, I didn't load the data set because my kernel restarted. So that's where error messages are helpful. It said DS isn't defined. I go back up here, run this, DS will be defined, and we're good to go. Okay, we're going to run this again. We're going to see what the output is. Okay. So we can see that it's nlat and long. That's what I want. But this is just the metadata. So I can type .compute. And it will actually compute this for me. Let's see what the output says. So there we go. Now I have this array and it has computed. You see all nans here, which means not a number, because these are just the first few values, and at the very corners of the plot, it's land, which is not a number. But you can set this equal to something. So you could say time mean values. And then you'd have access to that. Another option is load. These are very similar. They basically do the same thing. There are some minor differences, but and now if I mean values, now we see that we've evaluated all of this. You can also do, so time mean values, you can see here it's an X array data array. If you're used to working with a NumPy array and you just want to access a NumPy array, you can do .values. And then it returns, this is, now it no longer says X array, this is just a NumPy array, if you're familiar with that. So that's how we can access the actual values of the data set. Okay. We're almost out of time. I wanted to very quickly go through just a tiny bit of Dask if you're interested. If you have to leave, that's of course totally fine. Or if you have any questions right now, let me know. Otherwise, I'm going to just quickly show a little bit of Dask. So Dask is for parallel computing or distributed computing. There's this nice Dask tutorial that I've linked here. And Dask is especially useful for big data sets again. So a lot of these big climate data sets that you might use on the cloud. Dask is useful because it will run your computations in parallel. So you can run things much faster than you normally would. So I'm just going to do a little demonstration of this. And again, you can walk through this on your own. But here, we're going to show, I have defined two functions. So the first one is adding X and Y. And the second one is multiplying X and Y. And I've added this line here called sleep. This means that I am forcing the function to just pause and do nothing for 2 seconds. I'm forcing this function to pause for 1 second. I'm basically just doing this so that we can actually see the times, because this is such a small computation. We don't actually need to run it in parallel in normal times. So if I run this, this defines the functions. So they're defined. This is this fancy magic. We call this kind of cell magic. If you do %% time at the top of your cell, it will then print out how long it takes to run that cell. I actually use this quite often. So that's a nice little thing. And then I'm defining A to be the output of the add function for 1 and 2, B to be the output for multiply, and C to be the output for this multiply of A and B. So if we look back up here, how long do we expect this to take? Add is going to take 2 seconds, multiply will take 1, and then multiply will take another 1. So this should take 4 seconds. So let's see if that works. Wall time, 4 seconds. Nailed it. Great. Now, if we use Dask, it has this function called delayed, which means it doesn't run it right away. This is kind of goes back to this lazy loading. It delays the computation until you explicitly ask for it. So now, if I run the same cell, but instead we're going to make it a delayed function, going through this kind of quickly, but you can get a sense of what Dask does here. I'm going to run this, and now it says wall time 888 microseconds. That is very fast, and that doesn't make sense because our function literally says to pause for 2 seconds and 1 second. So this is an example of lazy loading. Dask has defined all of these things, they're ready to go, but it hasn't actually computed A, B, or C yet. So the way we do that, as I just mentioned, is we can call .compute. So now I'm just going to compute C. So C depends on A and B, which means it has to run A, which is 2 seconds. It has to run B, which is 1 second. Then it has to run this another multiply C, which is another 1 second. However, A and B are independent. I'm adding 1 and 2 and I'm multiplying 1 and 2. They are not dependent on one another. So Dask is smart enough to see that and to run the two of them at the same time, which means while this is taking 2 seconds, this will take 1, and then C can compute after that. So this should take 3 seconds to run, because we have 2 seconds plus the 1 second to run C. And there we go. It took 3 seconds and it gave us an output. So I think I might end things there. That was very fast, but it's just a little glimpse into how running things in parallel can help, especially if you have a very big computation that might take quite a long time. And you can read a little bit more here, more information. So I think, great. Okay, I'm just a couple minutes over. Are there any questions?
Yes, I have a question on Dask, for example.
Yes.
If I have 1 year of daily data, a global data set, like for example, a model 1/12 degree of resolution, and I want to use Dask to quickly read my data. What is, for example, can you just write an example of how to use it?
Yes, so it actually is relatively simple. So this is another aspect of Dask. So if we look here, this is this big climate data set we loaded. Under the hood, it's actually a Dask array already. So if you were saying to like quickly load, so if using Xarray and Dask together, if you use Xarray, you use Dask under the hood. Then you do this lazy loading and you will be loading the metadata. You don't actually load anything until you call .compute or .plot or .load or .values or something like that. So if you're just trying to, if you want to load, like if you have, if this is your data set and you're like, I want to see values of surface temperature, then you would just say dscm26 dot surface temp. And because this is a really big file, we can see here it's 260 gigabytes. So we can't load that in. You don't want to try. But I guess, is that your question? How to load that in with Dask?
Using Dask.
So the theory here is we don't have 260 gigabytes to be able to load in, that we don't have the memory, that much memory. So you don't actually want to just load in data. If you're trying to, you usually have some step. So you want to do a calculation that will end up being small. So if I want to actually use all of surface temperature, but then I just want to mean over time, then if you just call .compute on that, it will load, it will do the computation and spit out the mean over time. But you don't actually want to load that data first. Is there another example you have?
So in which time do we use Dask?
Like when to use Dask?
Yeah.
That is a very good question. So you don't always, so if you're using Xarray, if you use Xarray and you open up your data set and it says dask.array under the hood, then that's using Dask. And then you'll need to call this .compute. I think if you have a small data set, you don't need to use Dask. That's fine. So I'd guess in that sense, if you're loading a data set, you're doing computations, it runs quickly, it does what you want, you do not need to think about using Dask. Actually, in the Echo tutorial that we're going to do tomorrow, which I haven't uploaded yet because I'm still finishing, I'll have an example of using Dask on a big data set. So you would want to use Dask here if you're doing anything with 260 gigabytes. And there actually is kind of two different ways of using Dask. It's a little Dask. So you can use this interface and you can start up a Dask cluster. And you can see that here. So this is actually, giving you a lot more memory than what is in this current notebook. And you can, I haven't used this interface very well. You can scale up workers. Let's see if this works. So I said I want 10 workers and we'll see if this works. This kind of new interface is new. This is new on the sidebar, so I haven't used this much. But if it works, it should scale up the number of workers to 10. If I type this, it will, okay, so it's, okay, so that didn't work, that hit the kernel. So I will show in the Echo tutorial tomorrow an example of using this. And yeah, you can see some of the benefits. But if you don't need it, don't use it because it's pretty complicated and it adds a lot of extra steps.
Yeah, because I tried it during my PhD and I think it is sometimes when you use it and when you want to load the data, it was always crashing for me.
Yep, it happens a lot. I think everyone has a love-hate relationship with DAS because it allows you to do these big computations, but it's also, I mean, it's a pretty hefty, you know, piece of software, and it's pretty difficult, but things can work pretty smoothly.
Yeah.
So I'll have a demonstration tomorrow for that.
Okay, thank you so much.
Mhm.
And my last question is just to know if we can download the file. So do we have the right to keep it, what you just, the tutorial for us, like downloading?
Oh, yeah. Thanks. That's a great question. So you have all of this, all of these here. If you want to download this notebook, if you right click, then you can say download. You can do download and it will download straight to your computer.
Okay.
So if you create any images as well, you can create some figures that you save. So the satellite oceanography one, you'll end up saving a figure you can download directly.
Okay.
You can, on Thursday, I have a little introduction to Git and GitHub. If you don't know what that is, you can come by and find out. All of these are actually currently sitting on a GitHub, in a GitHub repository, which you can access and you can clone. So
great. Yeah.
Very good questions. Thank you.
Thank you so much.
Okay, are there any other questions from anyone here? Okay.
Hello.
Yes, hello. Hello, Mike? Is that you?
Hello, can you hear me?
Yes, we can. Can you hear us? Oh, maybe not.
Network is yeah. I don't know if you can hear me.
Yes, we can. Uh-oh, I don't think he can hear us. Okay, any other questions while we figure that audio out? Okay. We'll stop sharing. I will